Okay, good morning, everyone. I apologize for the homework that's due tonight. There was a glitch somewhere in the sync between Connect and Canvas, and it did not deploy. Yesterday morning I deployed it, but it didn't deploy until like afternoon, I believe. So if you're not yet aware, there is a homework due tonight. Very short, few questions. Shouldn't take longer than 15 or 20 minutes. But if you do need more time, if you get stuck, let me know and I will extend you without any penalty. Okay. Also, over the weekend, there will be another short homework in preparation for the quiz on Monday. So there's always a quiz on Monday on topics that we cover the preceding week. And so it's always at the beginning of class. And then the topics that we're going to cover today will be assessed on the quiz. And nothing that's going to be, too onerous or difficult. All right, let's go to our notebook. And I believe we stopped here. Chapter 2. Okay, as a recap, we will be working with semiconductor devices that will have both DC as well as AC signals. The notations that we use to write out the mathematical expressions. Uppercase, if it's all uppercase, it refers to DC components. If it's all lowercase, it refers to AC components. If it's a mix, uppercase and lowercase, then it's the total signal. Okay. An example would be something like this. It's a lowercase v for voltage and uppercase B and E. And so it's basically from a transistor, it's the voltage, the total voltage as measured from the base to the emitter. Okay. And we can write that as the DC base to emitter voltage plus the AC base to emitter voltage. Okay. This will be especially important when we perform the labs. Okay. When you perform the labs, if it's asking you to measure, depending on the notation that is being used, it might be asking you to measure the DC only, or it may be asking you to measure the total AC plus DC signal at that junction. Make sense, right? Mathematically, an example that you could come across would be something like this. Let's say total voltage 3 plus cos omega t, perhaps. Okay. There are multiple components in a signal, broken down, summation. Anything that is a constant would be DC. Or actually, let me write it this way. This is DC, and anything that is a variable of time would be AC. Right? AC would change its value as a function of time. So if there's a variable in there, in that component, that's AC. If it's a constant, it's DC. Any questions? Good. Okay. All right. Sources. I believe you should be familiar with these, but we'll do a quick recap anyway. All right. What's the difference between a voltage source and a current source? Anyone? Absolutely correct. Absolutely correct. Yep. A voltage source supplies a constant value of the voltage. A current source refers to a source that supplies a constant value of the current. Physically, they are the one and the same thing. They're the exact same thing. You all have taken labs in this building. You have worked with DC power supplies. If you've ever noticed, those DC power supplies, when they turn on, there'll be a tiny notation in one corner of the screen, CV or CC, constant voltage or constant current. It's the exact same power supply unit. You cannot have voltage without current. You cannot have current without voltage, right? Impossible. So voltage source, VTG, by the way, is my acronym for voltage. So voltage source supplies a constant voltage. I'll move this out of the way. So a voltage source will supply constant voltage, and it will adjust the output current according to the needs of the load circuit. So the current is variable in that sense. Okay. Now, when you're talking about constant value, you can run an AC source also in constant voltage or constant current mode. Function generators, you'd have to adjust it manually, but you can run it in constant voltage or constant current source. Okay. The value of that voltage or current is dependent on time, but we still say it's either constant voltage, constant current mode. So as an example, let's say you have a 1 volt source, 1 volt source, and you connect it to a 1 ohm resistor. What is the output current? 1 amp, right? Ohm's law. How about 10 ohm resistor? 0.1, right? So if the load changes, then the current is adjusted. So depending on the needs of the load circuit, the supply is still sending out 1 volt, but the current is now adjusted. Okay. And so for that reason, we set a current limit on real life power supplies. Theoretically, it does not matter. You could connect a 0.1 ohm resistor at the output terminals, and you could say it's going to supply 10 amps, but you would end up burning out your resistor or your circuit. And so you'd set a current limit when you're running in constant voltage mode. If you're running in constant current mode, you would set a voltage limit, because you do not want your power supply to burn out. If it's 1 ohm, you would get 1 volt at the output. If it's 10 ohms, it requires 10 volts to keep the constant current at 1 amp. Okay. So we set OCP, which is over current protection, OVP as over voltage protection. Make sense, right? Any questions? Okay. So the next question is, what is the difference between the circle and the diamond? Absolutely. So the circles designated for independent sources, and the diamond notes that it's a dependent source. A dependent source can be anything. Typically, we use dependent sources for models. Remember, I said we will use many different models to describe the behavior of our semiconductor devices. So diodes, transistors, we'll have several different kinds of models, and each one of those models will incorporate a dependent source. Okay. But let's use like a real life example. So a dependent source is a source that will supply its rated quantity, but it depends on some other quantity in some other part of the circuit to supply. Quite a mouthful, but let me explain. Here we have a voltage divider circuit. You have resistors connected in series, so it divides the voltage. Let's say you apply 3 volts between the 2 output terminals. Okay. That's your ground. And let's say this is X plus minus. Let's say this is Y plus minus. If you apply 3 volts, and let's say this is 1K, 1K, and 1K, to keep things simple. What is the voltage across each one of those resistors? 1 volt, right? Equal division. So what is the voltage at point X? 1 volt, right? So X is 1 volt. How about Y? 2 volts. But now, if this 3 changes to 6 volts, what is the value of X? 2. Y is 4 volts. Points X and Y are dependent voltage sources. They are supplying 1 volt or 2 volt output voltages, but those output voltages depend on some other quantity in some other part of the circuit. Make sense? So we could describe X as being Vs. Let's say this is Vs. You would say it's Vs divided by 3. That would be the equation that describes X. And Y would be Vs divided by 2/3, 0.6. Make sense? Right? So X will supply a voltage, but it depends on Vs for its output value. And so we can represent X as a diamond with a plus minus in the middle. Now for transistors, we say the transistor has an amplifying action. So it supplies a output current at the collector, but that output current at the collector depends on the base current. And so that's why it's very helpful and useful. Plus and minus indicates it's a voltage source. The arrow indicates it's a current source. The dependency can be of two kinds. It could depend on a voltage or it could depend on a current. And I assume you all learned all of this 1 year ago. Remember, kind of. So if this is controlled by a voltage, this would be a voltage controlled voltage source. On the left, we have a dependent voltage source, and it could be dependent on a voltage or it could be dependent on a current. And so we would write, we would describe this, the first one, we would describe this as a voltage controlled voltage source or a current controlled voltage source. On the right, the current sources, we can write it as a voltage controlled current source or a current controlled current source. The first C is controlled, second one is for current in all of them. Okay, Vs is voltage source, Cs is current source, Vc and Cc are voltage controlled and current controlled. X and Y are examples of voltage controlled voltage source, Vc, Vs. All right, 10-second pause. Think over all of that, write it down. Let me know if you have any questions. If you're online, please feel free to interrupt if you have a question. So do not write anything in the chat because I would not be able to monitor it. We do have a speaker in the class, so I'll be able to hear that. All right, any questions before we move on? Okay, so approach. This has been my standard approach for several years, decades. And it's also outlined in the book with some modifications. This is what I use. When you have a given problem, okay, problem could be a simple statement in words, could be a circuit diagram, could be a graph. Identify the problem statement, read and understand. That's the absolute first thing. Next thing, always I'm fond of stating is extract as much information as you can from the given problem statement. And when I say extract as much information, meaning you read the statement, words, and then look at the circuit diagram. Oftentimes, there are tiny details in the circuit diagram. Okay, and I will show that with an example. Also, sometimes there is graphical illustration of the source, whether it's a voltage or current, or maybe any other physical quantity in that problem. Okay, so we have to pay attention there too. So identify the problem statement, to read through the problem statement, understand everything that's given in the problem statement, extract as much information as you can, make your assumptions, outline your approach, and then solve using any analysis techniques that you deem suitable. Okay. You make an assumption at the top, you perform your analysis, and then you look at your results. Then you compare your results to your assumptions. Are those assumptions valid? If the assumptions and your results don't match up, then you have to go back to the, well, not quite the beginning, but you have to go back to your assumptions, change an assumption, perform a second analysis, look again at your solution, verify whether it matches up with your assumptions. If it does, then you're done. If it does not, then you iterate one more time. And so there is a technique that we call as iterative analysis. We make an assumption depending on the possible states in the circuit, and then we perform an analysis and verify whether a solution is correct or not. Okay, and that is basically the numerical approach. We have several different models for our devices that describe our device behavior, right? These models mathematically are described with equations. Sometimes they have 2, 3, 4, 5 variables. So the more variables you have, right, the better you're able to describe your device behavior. But again, it's an iterative process. You have to keep performing your analyses until you end up with the correct answer. And so here, again, I would say this is the absolute first, second, most important, and then assumptions and verifying results kind of moves in a circle. Your your results must match with your assumptions. If they don't, then you need to perform it again. All right. And then, of course, simulations versus calculations. You have theoretical hand calculations. That is the whole point of learning circuit analysis. And then the software that would allow us to perform simulations. Yeah, PSpice, LTSpice, MATLAB, lots of other powerful software tools that you can simulate your circuits. All right, so example. And this also goes a little bit into the next slide. If you have, this is a random circuit, so you don't have to draw it out. But let's say you have a circuit that looks something like this, right? There's values for resistors, inductors, capacitors, doesn't really matter what it is. I drew it with a very small font for a purpose. Let's say you perform your analysis, you get your answers. Voltage across the resistor is like 5 volts. Output voltage at the far end of the circuit is like 3 volts. And the current through the capacitor is 1.5 milliamps, for example. Now, everything could be correct about your analysis and your result. Your assumptions are valid. Your analysis technique is valid. It's correct. The method is correct. Your approach is correct. Your calculations are correct. Your final result, your final value is also correct. Final value, I mean, the value for 1.5 is also correct. But if you miss the current limit of 1 milliamp from the power supply, right, your final answer would then be incorrect. Everything is correct about your approach, about your calculations, everything is correct. But if there is a current limit specified in the circuit diagram of 1 milliamp, there is no way that the capacitor current or any current in that circuit for that matter would be higher than 1 milliamp. Does that make sense? Right? So when I state extract as much information as you can, it's meaning basically pay attention to details. And that's also something that employers look for in candidates. They always state candidates should be attention to detail. So if there is a current limit, voltage limit, numerical, the values of components in there, if you miss one tiny detail, your final answer would be incorrect, even though everything else is correct. Make sense? Right? Similarly, if there is a graphical description, and I used to make this mistake early on. What is the unit for time? Seconds. But unit prefixes are often used because we describe our time dependency in milliseconds and sometimes in microseconds. The Greek letter mu is used for micro. Okay, micro, 10⁻⁶. So if I've done this often, not recently, but I've done this in the past. I've performed the reason this sticks with me is because I've performed the same mistake several times. So instead of, typically I'm used to like just seeing milliseconds on there, but there was one problem where it's like microseconds, and I would go through everything, my analysis would be correct, and there would still turn out that the answer is incorrect. It would not match up. And that's when I realized I took milli instead of micro. And then of course you have units here on the y-axis also. And so that's also something that you would want to pay attention to. Okay. So again, problem statement, extract all of the information. That information could be in the words, it could be in the circuit diagram, it could be in graphical illustration. And continuing on that approach, you would think about what is a reasonable number in your circuit. Okay, what is a reasonable number in your circuit? These three: first, voltage limits and current limits for that matter. So power supply voltage limits and current limits. AC signal limits and circuit's current range cannot exceed the supply energy source. If your circuit has a 10-volt source, voltages in the circuit cannot exceed 10 volts. Energy cannot come from thin air. Think back to 1 year ago when you were performing op-amp analysis, right? An op-amp could have a gain of 100. If you apply 1-volt AC signal, theoretically, yes, we could get 100 volts at the output. But that energy does not come from thin air. The energy comes from the DC biasing voltages that you connect, the plus minus voltage supplies. If all you're connecting to that op-amp is plus minus 10 volts, then your AC output voltage cannot be more than 20, right? Even though the gain may be 100, your output voltage cannot be more than 20. Make sense, right? This statement is true with a few exceptions. Such as a clamper circuit, where it is possible to get higher voltages. You'd apply a AC source or signal, let's say for 10 amps. Not 10 amps, 10 volts. And then voltage across the output could be larger than 10 volts. And the reason is because there is a capacitor in the circuit. 1/2 cycle, the capacitor charges. It reaches a full charge, 5 volts, 10 volts, depending on the circuit configuration. The next half cycle, it's cut off. So when the next half cycle comes along, the capacitor stored energy is added on to your 10 volts, and then the output voltage is larger than 10 volts. That's something we'll look at in chapter 3. It's called a clamper circuit. That's also used in function generators to apply DC offset to your AC signals. You'll remember some experiments, you apply a DC component known as a DC offset in your function generators. That requires a clamper circuit because it clamps your AC signal at a positive DC value or a negative DC value. Okay, so those kind of circuits, it is possible to obtain larger voltages and currents. Okay, any questions? Questions? No, we're doing on time, 9:37. Calculated component values. Yeah, with a few exceptions, again, generally speaking, if you calculate any quantity, whether it's a voltage or a current, or a resistor perhaps in your circuit, those should look reasonable to you in the sense that they should not be fantastical values. You would not expect to see kiloamps in a regular small circuit, right? If it's like a 10-volt circuit or a 15-volt circuit, you would not expect to see kiloamps. You would expect to see milliamps or microamps even, maybe not nanoamps or femtoamps. Neither really, really tiny nor really, really large. So some nonsensical, fantastical value. That's what I call them. So kiloamps or maybe milliohms perhaps, right? That is what is meant by reasonable numbers. All right, circuit analysis. How many circuit analysis techniques did you learn? Lots of them, right? Apart from these three, you learned about voltage division, current division, Thevenin Norton, node voltage analysis, mesh current analysis, superposition. Do you all remember all of those? Hopefully. I have confidence. But they are all based on these three. Okay, we don't need anything more than these three. All of EE is based on these three equations: Ohm's law, KCL, KVL. Everything else is a combination of Ohm's law and KVL, KCL. You do nodal analysis. Node voltage analysis is basically Ohm's law plus KCL gives you node voltage analysis. Ohm's law plus KVL gives you mesh current analysis. Superposition is simply breaking up the circuit into individual pieces with only one source active at a time. Again, then you can solve it using any analysis technique you want. Voltage division, current division, again, based simply on Ohm's law. Every student has learned their own way of applying KCL and KVL, so I'm not here to redo any of that. Feel free to continue doing what you're doing. If you have any questions, reach out to me. I'd be happy to explain outside of class. Okay. I just want to do a quick review of current and voltage division because that is something that you'd be required to apply quickly and correctly when you're performing analyses of of these models that we're going to learn. So voltage division is when you have a series connection of resistors and you have a voltage applied to a series connection of resistors. The current remains the same, obviously, but the voltage gets divided. And the voltage division allows us to skip a couple of steps. Voltage division is derived from Ohm's law. And here in this case, we can directly write the voltage appearing across each resistor. Let me call this, okay, it's V1. V1 is a fraction of V total, and the fraction is given by the ratio of the resistor to Req. Req in this case is the total equivalent resistance of that series network. Okay, R1 plus R2 plus R3 plus R4. So voltage division principle states when you apply a voltage to a series connection of resistors, a fraction of that supply voltage appears across each resistor. And the fraction is given by the ratio of the resistor to Req. Quite a mouthful, but the mathematical equation is quite straightforward. V1 is Vt times R1 divided by Req. Ring any bells? How about current division? What's the equation for current division? Let's first write out the Req. Req is the reciprocal of the sum of all the reciprocals. So what's the current division equation? In words, it's quite the same thing. When you have a parallel connection of resistances or components, voltage remains the same across those two nodes, but the current gets divided, and a fraction of the total supply current appears across each, appears through each resistor or through each branch. And the fraction is given by the ratio of Req to R1. It's flipped. That's the only difference, right? Because for parallel connections, Req is 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4, so on and so forth. So when you derive it from Ohm's law and you plug in Ohm from Req, you plug it into the equation, you would get Req divided by the resistor of interest, which is R1, R2, R3. Make sense? Hopefully you all remember this. There's also another way of applying, but this is the easiest. Okay. There is another way of applying current division, but that's a little longer, and frankly, I don't prefer that. This is the easiest. Any questions? One thing I'd like to point out, and this is just a little bit of tangent. Series connection of resistors, you simply add up. If this was series, it would be 10 plus 30 plus 60, resulting in 100. Our human brains are not, we don't pay attention because human brains automatically recognize 100, which is larger than any of these three resistors. Because we know automatically that if you add something to another quantity, the result will be larger. Am I making sense so far? 100 is larger than 10, 30, or 60. On the other hand, if it's a parallel connection of resistors, the resulting Req will always be smaller than the smallest value in that resistor network. So 10 in parallel with 30 in parallel with 60, the resulting Req should be less than 10. If it is larger than 10, then your answer is incorrect. Okay, this is not something we automatically think about. We have to train our brains to notice that. Okay, the last and most important topic, Thevenin and Norton. In the late 1800s, Leon Charles Thevenin, the French telegraph engineer, he postulated a theory, stated that if you have a linear circuit, a large linear circuit comprising of multiple sources, multiple resistors, you could reduce it all down to one single voltage source. You could represent a large circuit with one single voltage source and one single resistance, only two components required. So circuit could potentially be hundreds of thousands of components. You could represent it as one single voltage source in series with that resistor. The theory was published and the theorem came to be named after him, known as Thevenin theorem, or Thevenin's theorem, if you will. The voltage is referred to as Thevenin voltage. Resistance is referred to as Thevenin resistance. Very powerful concept. We will use this again and again and again for our analysis. Okay, as an EE, you should be very closely familiar with determining Thevenin and Norton. Okay. A few decades after Thevenin's theorem was published, there was an American engineer working at Bell Labs by the name of Edward Norton, not the actor. He's not that old. And he was working with a lot of audio equipment. And so it's useful to work with a lot of current sources when you deal with audio analysis. Okay, audio circuit analysis. So he postulated his own theory based off of Thevenin's theorem, and he stated that you could take that same large circuit and represent it as a current source in parallel with that same resistance. And that theorem came to be known as Norton theorem, and the current was known as Norton current. The resistance is still the same, Thevenin resistance. And because they are both equivalent of a larger circuit, they are also equivalent to each other. And the relationship is defined by Ohm's law. VTH is equal to IN times RTH. You will often be required to quickly and correctly analyze a network of resistors and determine the Thevenin resistance. Like 2 or 3 resistors connected as input to a transistor, analyze it to determine Thevenin resistance as seen by the transistor. Okay. The way to analyze the circuit, let's see. What is the setup? Right? What is the setup? In this example that I use, when I teach circuit analysis, I use this example, and I'm stating that we wish to find a value for R6. So if you're trying to analyze the circuit as seen by R6, you have to remove R6 from your analysis. And you remove R6 from your analysis, and you're left with open terminals. I simply call them V out plus and V out minus. It's just the notation I use, nothing else. Right? You analyze the circuit between V out plus and V out minus. Now, theoretical analysis takes a while to go through, especially if it's a large circuit. Actually measuring the voltage takes like 10 seconds. You build your circuit, turn on the power supply, connect the multimeter at the output terminals, put it on voltage measurement mode, done. You measure the voltage, that's your VTH. But actual analysis takes a long time. So you don't have to draw this out. I'm just doing this as a refresher. If you're performing analysis to determine Thevenin voltage, you would have the circuit. And all you're going to do is analyze the circuit to find the open circuit voltage at those output terminals. You remove R6, you perform your calculations to determine the open circuit voltage at the output, and that will give you your Thevenin voltage. Hopefully this rings a bell. You modify the circuit. Once you modify the circuit, you choose any analysis technique you want. Node voltage analysis, mesh current analysis, Ohm's law, KVL, KCL, apply them in any order you want, your choice, and then you determine the output voltage that gives you the Thevenin voltage. Let's take a 5-second pause. Let me know if you have any questions. Any questions? Ten minutes left. Okay. How about Thevenin resistance? What is the setup of Thevenin resistance? The measurement terminals are still the same. You measure the resistance at those output terminals. RTH is measured between these terminals. All you're doing is you're determining REQ as seen from the perspective of those terminals. And REQ, the total equivalent resistance, gives you your RTH. If you are trying to measure resistance, there should be only resistors in the circuit, nothing else. And so we replace all independent sources, we reduce them to 0. Any value the source has, we reduce it to 0. And reducing it to 0 means you remove all the sources from the circuit and you replace the voltage source with a short circuit. And you replace the current source with an open circuit. Essentially, you just remove it from the circuit. That's it. And then you calculate your Req between those terminals. That Req will be your RTH, Thevenin resistance. Okay. Does it ring a bell? 2 bells, 3 bells. And then Norton current. Same thing again. I won't draw the entire circuit, but you have your output terminals. Current needs a pathway to flow. And so we short the output terminals and we calculate the current flowing through there. That gives you your Norton current. IN. Okay. So current needs a pathway, so you have to place a short in between those terminals. And that gives you your Norton current. Any questions? Does the setup make sense? Yes. That's on the next slide. Good thinking. That was my next question. So what do we do if we have a dependent source in there? Because we cannot reduce a dependent source to 0. So if you wish to find RTH, we cannot ignore that dependent source. And let's go to the next page. Okay. So if we wish to analyze this, we first look at the dependent source. In this case, this example has a dependent current source. And the dependent current source depends on a current in a different part of the circuit. The equation is given by beta I1. The dependent source depends on I1. Okay. All we have to do is to treat that as any other current in the circuit and write our equation. Okay. Now, if we wish to solve this, I would choose either mesh current analysis or node voltage analysis. Mesh current analysis would require me to assume mesh currents. Node voltage analysis, we assume a reference node, typically the negative end of a voltage source, and then we perform our analysis. We are asked, or we want to find VTH, right? So if you wish to find VTH, in this case, VTH is equal to VO. And VO is the same as the voltage across RS. So I will make few assumptions. Assumption would be that I have I1 coming through here. I have this beta I1 coming up too. And this node and combines to form IS that is flowing through RS. Circuit analysis, theoretical circuit analysis, it does not make any difference what you choose at the beginning. I am choosing IS to go down because that makes the most logical sense. If IS was going up, my analysis would still be correct. Okay. So if I choose node voltage analysis, I can write an KCL equation. So apply KCL and I can write I1 plus beta I1 is equal to IS. Two currents entering, one current leaving. Right? I1 plus beta I1 is equal to IS. Make sense? Right? Then we describe each one of these currents in terms of the node voltages. So the node voltages for I1, which is across the resistor, this is VI, this is VO. Is it VI minus VO or is it VO minus VI? Current is like any other physical quantity, always flows from high to low. If both points are the exact same electric potential, there is no current because the voltage is 0. One point has to be higher. So if current is flowing from left to right, that means the point on the left is higher than the point on the right. And so it's VI minus VO. So I1 would be VI minus VO divided by R1. And then the same thing here, because I already have my equation, now the unknown is eliminated. Then IS is coming down from the top, so it's VO minus 0, because my reference is at the bottom node, has a value of 0 volts. So VO minus 0 divided by RS, that is my equation. I treat the dependent source as any other current. If it was a dependent voltage source, I would perhaps write a KVL expression, right? Because it's a dependent current source, I treat it like any other current in the circuit. Plug in the values, and if you notice the equation, resistor values will be given to us or known to us. So we plug in all the known values, which is the resistor, VI. The only unknown left in the circuit is VO. You solve for VO, that is your Thevenin voltage. 2 minutes left. Let me just talk quickly about Thevenin resistance. So again, I won't draw everything out, but at the output terminals, I would apply an energy source, call it V, and the energy source would supply current I to the rest of the circuit, right? So the rest of the point is we want to find the Thevenin resistance of this entire circuit. So Thevenin resistance means between these points, this should be equal to a resistor. So if I connect a voltage source to this resistor, V and I, and this is Req, V divided by I should give me Req. So you apply a voltage source, a known voltage source. You can choose any value you want. You calculate the current I flowing through the circuit, and then Req or RTH would be V over I. That's how you would solve it. All other conditions still remain the same. If you have independent sources in the circuit, you reduce them to 0, meaning this voltage source VI here would be 0, replaced with a short circuit. Norton current also the exact same way. You take the output terminals, you place a short circuit wire between the output terminals, you solve the circuit exactly as I did here. You write an equation. It's even easier because the short will take out RS for the Norton current. Okay. This is an example in the book. So please review. Everybody has access to the e-text. It's on the left side of your Connect page. Does anyone notice that? There's access to the e-text. So I think it's example 1.4 or example 1.5. There is an error in that example. I believe they first write VO minus VI, but it should be VI minus VO. Okay. So review that example. Reach out to me if you have any questions. I will be available all weekend long via email always. And then if you need, I can also meet on Zoom. Okay. Quiz on Monday, first 15 minutes of class. I will post an announcement with all the details. It'll be based on the homework assignments that you have done. 15 to 20 minutes of work time, and then 5 minutes after that to scan and upload your results on Canvas. If you are taking the quiz online, you can do so. It's open book, open notes, open internet. But your cameras must be on for the duration of the quiz. All right. So I'll bid you all a good weekend. I will see you all on Monday.